Yes, so thanks to Barbara for inviting me, and it's actually good that this got delayed by 1.5 years, because now I got some new and unpublished, thanks to Thorsten and his postdoc Eivind, I got some new and unpublished results to present, and hopefully exciting results instead of just published things. Yes, so dynamic topography, in principle, it's quite simple. It's when you have mantle convection, you have upwellings pushing the surface down, and downwellings pushing it up, and downwellings pulling it down. So that's in principle quite simple, but I'll come back to the complications later. So so this just shows one region where you have obvious dynamic topography in East Africa, material pushed up. And also in this figure, it shows some deep erosion, which is something, when you get to time-dependent topography, something that will be important to be considered, especially in future work, to the interaction with surface processes. Because when you erode this dynamic topography, then obviously the rock uplift can be much increased, and by just simply uplifting material. Right, so this is a maximum amount of dynamic topography on the Earth. It's on kilometer scale, 2 kilometers or so. The typical scales are more like hundreds of meters scale, but it's also important because most of the continental actual topography is near sea level, so it obviously plays an important role towards which regions are below sea level and which are above, where is erosion, where is sedimentation, and what are the ocean currents. So that's something in this work with Thorsten and Eivind, we start looking at those things. Right. So what makes things about dynamic topography a bit more complicated is that, for one thing, the observed topography is largely non-dynamic, so it's due to crustal thickness variations. And then also conceptually, it's difficult to say which part you count as dynamic topography. So there are different definitions, and this causes some confusion. But I think as long as you're clear about what you mean, it's not a problem. And so I will tell you now what's my definition of dynamic topography, or what I tend to include. Yes, and another conceptual difference is a difficulty is that when you have close to the surface, then this dynamic topography, basically becomes the same as isostatic topography. And then some people would say, well, if it's isostatic, then it's not dynamic, so we have to exclude it. But so that's a conceptual problem with it. So the causes for large-scale topography can be broadly split up into 4 contributions. One is due to crustal thickness variations. This is the largest contribution, and that's the one that's obviously not dynamic topography. So that's what everybody would subtract. That's shown here as delta rho 1. So this dark gray color, that's a crust. So thick crust gives high topography, like ocean-continent contrast. Then the second contribution is due to ocean cooling with ocean lithosphere cooling with age. And then we have seen in the talk by Steve Grant that some people include this in dynamic topography. So in my case, I will subtract it. But as long as you do this consistently, subtract the same contribution, or say exactly what you subtract, it's entirely equivalent to do it either way. It's just when because this ocean lithosphere cooling with age is a very large contribution, which we think we understand well, so I find it convenient to take it off the dynamic topography, such that the remaining signal is more relevant for the mantle underneath. Then thirdly, there are thermal and compositional variations in the lithosphere, because the lithosphere is basically isostatic, so some people would exclude this, but I keep it in my definition of mantle-derived topography. So then it may be not good to call it dynamic topography, but mantle-derived topography, because in order to exclude it, you would need to know how thick the lithosphere is, which adds another uncertainty. And fourthly, there is the contribution to the mantle convection from beneath the lithosphere, which is the most obvious contribution to dynamic topography. So at shallow depth, isostatic and dynamic topography are very large. So it's not are very similar, And so it's not important to make the distinction for present day, but for time changes, it becomes important because the contribution inside the lithosphere obviously moves with the plates, and so there's no change at the point moving with the plate, but the contribution from the mantle doesn't move, so it can cause uplift and subsidence, even it doesn't change, but just due to the continent moving over it. Right, so in order to check the quality of our dynamic topography models, we compare a model of residual topography that is obtained by subtracting, in my case, the contributions 1 to the crust thickness variation and 2 to the ocean floor topography from actual topography. So it's the observation-based estimate of dynamic topography, and we compare this with a model of dynamic topography due to the contributions from inside the mantle, including the lithosphere, that's obtained from a mantle dynamic model based on seismic tomography. And importantly, I include all anomalies from seismic tomography, also the ones due to ocean floor cooling, but then I subtract the same contribution due to ocean floor cooling, which is obtained from a seafloor age model, and in order to make this entirely consistent, how those two contributions are computed, and then these are compared. Now, coming to the first estimate based on observations, as I said, I start with actual topography, and then I subtract the crustal isostatic topography. So in this case, I take the crust 1 model, computed based on densities and thicknesses of crustal layers, and then I get a non-isostatic topography, which clearly shows the ridges. It also shows ocean-continent contrast, that continents tend to be a lot lower than oceans. Now, as a next step, as said, I subtract the ridge topography, and that also means that you have to assign to the continents where you don't have a seafloor age, you have to assign to the continents another age, and I use this 200 million years age in order to get mostly rid of the ocean-continent contrast. So that's an arbitrary choice, but as long as you do things consistently, it's not a problem. But then it means that you get more or less similar average on continents and ocean, and no strong contrast, which makes it easy to look at contributions from deeper down. Right, so this is our observation-derived dynamic topography. And then as a final step, you see here, you see some features in the ocean which are due to hotspot tracks, and they're probably not dynamic either, but due to crust thickness variations. So those are, I apply some mask to take them out. And then this is my final estimate of the observation-derived dynamic topography. Okay, so we compare the model of residual topography with a model of dynamic topography. And however, density anomalies in the continental lithosphere have both thermal and compositional origin, and therefore we cannot simply scale dynamic topography. Scale them in order to infer dynamic topography. So that's also something which Steve Grant yesterday already talked about. So we need to derive also a lithosphere thickness models which we can use to distinguish between the contributions from the lithosphere and the mantle underneath, and then take out or then treat the lithosphere differently, where we don't simply scale from seismic tomography. Right. So in order to compute lithosphere thickness, I also base this on seismic tomography, and in this case I use one of the models from Steve Grant, just showing here as an example cross-section through Africa. So this is the upwelling under Africa, and these features are the lithosphere. And you can already estimate from the tomography model what would be the lithosphere. But the point is that it's not just I don't take a constant velocity variation as the base of the lithosphere, but I convert this velocity variation to a seismic velocity variation to a temperature variation, and then I add to this temperature variation a reference temperature profile, which is meant to correspond to the global average. And then I take for the inferred total temperature profile, I take a certain temperature value as a depth of the lithosphere. So this can be also done by computing where this seismic velocity variation intersects this reference profile, right? And So in order to get a thin lithosphere, you would have to have a very low seismic velocity. Then for low seismic velocity, then you get this intersection at shallower levels, and for high seismic velocity at deeper levels, right? And details are explained in these papers here. Yes. So yeah, and there are two free parameters in this determination. So one is basically the vertical extent of this curve, and then the horizontal extent. And in order to determine those, I match the lithosphere thickness model in the ocean, where we think we have an idea what it's like with a half-space cooling curve. And I do this here. Here are 4 examples for tomography models shown, and in all cases up to about 120 million years, you can get a fairly good fit with this half-space cooling profile if you adjust those parameters. So after adjusting those parameters, then I use the same model then also to determine lithosphere thickness for continents. Now this is the lithosphere thickness model I came up with then, and it's sort of makes sense. So it's mainly based here on the Schäfer and Lebedev tomography model at shallower levels, and at Grant's model deeper down. And yeah, so you see like ridges, and you see cratons, and yeah, other people have shown similar models. So that's, I think, is with tomography you can get some fairly good idea of lithosphere thickness, which is also consistent with geologic evidence. Now, in which part of the lithosphere, now the question is which part of the lithosphere can we just convert seismic velocities to temperature, and which parts we have to exclude. Now we did in this paper with Thorsten Becker, what I did is I inferred the temperature profile clustered for certain lithosphere thicknesses from this tomography model. So I just take the vertical profile and cluster them for the inferred thickness, and then compare with the theoretical temperature profile. So for this, assuming this, what is it called, error function profile. And I find that always for the lower part of the lithosphere, up to about 150 kilometers or so, there is a very good fit with this inferred temperature profile. Only in the upper part, it deviates. And for thinner lithospheres, it's the same for both oceans and continents. So oceanic is blue, continental is red. Then for very thin lithosphere, you see that for the oceans, you get higher temperature. So that means like there's probably this high temperature channel. But here, that if this inferred temperature differs from this expected temperature, so that probably means that it is, the seismic velocities are not due to temperature variations, but due to compositional variations. So in the end, I decided I take wherever how thick the lithosphere is, I take in the uppermost 150 kilometers, I remove sort of the seismic velocity variations, and instead I impose a given density variation, which is another free parameter in my inversion. Right. So yeah, just to show improvement in tomography models, this is the geoid kernels plotted in this way as spherical harmonic degrees versus depth. So the kernel basically says the contribution is a depth and density anomaly at a certain spherical harmonic degree and a certain depth, what this contributes to the geoid. And if we compare the correlation of the seismic tomography with the geoid for S mean, you see that there is some good correspondence of this red blob with this one, and this blue with this, and blue here. But for higher degrees, this correspondence disappears. So that means it seems like at this spherical harmonic degree range throughout the mantle, this S mean model would give a good representation of density variations. But then you see for the higher degrees, this SL, this Schäfer and Lebedev model, it gives a much better correlation at higher, at shallow depths. So that would indicate that this is a higher resolved model at lithosphere depths. Right. So this is the reason why I show results now which are based on this Schäfer and Lebedev model, because that includes surface waves, and so that's good at lithosphere depth, which is most relevant depth for dynamic topography. Right. So again, coming back to this cross-section, so this is the features, the regions where I possibly exclude seismic velocities and replace them by a given value. So this is here, this is density variations, and everywhere else are scaled by seismic tomography. But in the lithosphere, I take this off, and also in the lowermost mantle, but that's not relevant much for dynamic topography. Then I use this, in this case it's a little bit simpler because here I excluded just the uppermost 200 kilometer, but in principle then I can use this remaining density variation with a radial viscosity profile and a scaling from seismic velocities to temperature to compute mantle flow. And then this mantle flow, then this gives me this dynamic topography, right? And the way topography can simply convert it in this case, when you have only radial viscosity variations, you use these topography kernels. So again, for a given spherical harmonic degree and depth, the kernel tells you how efficient topography is generated. So that means in the lower mantle, mostly the low degrees have an effect, whereas for higher degrees, it's only the upper mantle has an effect. 5 minutes left. Okay, then I have to speed up. Right. Then this is the, so also I don't take a given viscosity profile, but I vary the viscosity in these layers. The shape is based on mineral physics. And then finally with the optimized model, also with the optimized models, and with a given lithosphere density anomaly, I can then get this kind of fit between the model-derived dynamic topography and the observation-based dynamic topography. And yeah, here is the overall feature. So the ratio, particularly for oceans, the ratio is too high. Coming back to what Thorsten alluded, that you probably need this low viscosity underneath the oceans to reduce the amplitude, but the pattern is correlated with factor 0.56. In the continents, the ratio is okay, and the correlation is also higher. And you can see that there are also many detailed features that match, and some other places don't match so well. For example, here, focus on Antarctica. It matches in West Antarctica, and many other features match, but in East Antarctica, there is a mismatch. Right. Now, can you look at the spherical harmonic degree? So basically, the largest misfit at spherical harmonic degree 2, and then we can distinguish between lower mantle and upper mantle contribution. The degree 2 mostly comes from the lower mantle, whereas higher degrees mostly come from the upper mantle. So, so I think I have to skip this now, this part about Venus, since I'm running out of time, in order to get to this time-dependent part. So time-dependent dynamic topography, again, I start with a present-day anomaly, and then I use this present day to compute the flow field and backward advect density anomalies. So going back in time, this is now shown forward in time, slabs sinking and anomalies rising. And the main, one thing is that the amplitude goes down further back in time, because basically material is extracted down of the mantle. So backward in time, the slabs get up to the surface, the positive anomalies close to the core mantle boundary. And so you remove anomalies, but so there are improvements on this, but in this case, so for the mid-mantle anomaly, I think it's more or less okay, at least if you not go further back than like 50, 60 million years ago. So let's just skip the next models. And now we come to this. This is collaboration with Eivind and Thorsten, that now we combine these dynamic topography model with the motion of the continents in order to compute how at a places moving with continents, dynamic topography has changed. So for example, you can see this now, if you look at India, it starts at 50 million years ago very much red, means high compared to present day, and it's mainly because India used to be above this region of high dynamic topography, now moving to low dynamic topography. So in this case, the change of dynamic topography is due to due to the motion. In case of East Africa, it's basically because due to this backward advection, this large anomaly under East Africa only comes up to the surface very recently, which I'm not sure whether this is real, but if you backward advect, then you always get this very recent uplift. So you would have to somehow reconstruct the anomaly further back in time, but it's of course difficult because the heat has been diffused away, and so it's difficult to reconstruct it back in time. Right, so we want to apply this to compute the Paleo Topography. Here you have 40 million years ago, you still have the seaway open, so you get more currents, and then 30 million years it starts closing, and then 20 million years is shut off, and this is obviously influenced by how much dynamic topography there was in this region where this seaway was. And yeah, just finally, there are also in order to move things further, there are also contributions due to thermal diffusion, as I said, which you could, at least for the recent times, you can infer this from the anomalous heat flow. Then you could, at least for recent times, you can correct for that. And under uplift in subsidence, under consideration of erosion, it changed, which is important for time dependence, is also, like, for example, if you have rock uplift and surface uplift rate equal, then this term falls off, then the radial velocity is simply stress change divided by gravity and density. Whereas if you say rock change and if you say surface uplift is 0, so everything's eroded, which is uplifted, then you get the rock uplift is stress change divided by gravity, and the difference between mantle and crustal density, then it's much larger. So in any case, when partly eroded, it's somewhere in between. So this is why it's important to consider surface processes. So it's something which I think is still underexplored. And finally, just indicating there is also, besides this local dynamic topography effect, there is also this global effect. Like when you have continents moving from regions of high topography to low topography, then the volume of the ocean changes, and then this also causes a contribution to sea level apart from this local effect due to the land uplifting and subsiding. Right. So yeah, I think I won't go into this. So basically, I don't have a conclusion slide, but the main conclusions are that for one thing, there are still some very basic things that are not well understood. One is the viscosity structure, which I just take one model, but we've seen yesterday there are many different viscosity structures. And there's also this problem that the dynamic topography, especially at very low degrees, is much over-predicted. And you cannot just reduce the amplitudes of the density anomalies, because this same model gives a very good fit to the geoid, which also has a contribution from the surface uplift. So that's something which I think is some very basic things which are still not well understood. But then there are also some further developments which are also, I think, underexplored, in particularly this time dependence and decoupling with surface processes. Thank you.